Where is everybody? Enrico Fermi reportedly asked this question during lunch at Los Alamos National Laboratory in the summer of 1950. Sitting with him were physicists Emil Konopinski, Edward Teller, and Herbert York. Earlier, the group had been joking about newspaper reports of flying saucers and a New Yorker cartoon in which extraterrestrials were stealing garbage cans from New York City. Then, the conversation moved on.
Without warning, Fermi interrupted with a question that seemed unrelated to what they were discussing. Where is everybody? His colleagues immediately understood what he meant. The Milky Way is enormous, ancient, and filled with stars. If technologically advanced civilizations are even moderately common, some should have appeared millions or billions of years before humanity. Even without faster-than-light travel, they would have had enough time to spread through much of the galaxy.
Yet we see no confirmed alien spacecraft, no artificial stars, no extraterrestrial cities, no verified messages, and no undeniable artifacts left behind by an older civilization. The universe appears as silent as it is vast. This apparent contradiction became known as the Fermi paradox, although Fermi himself never published a scientific paper formally presenting it. The modern colonization argument was developed more explicitly by researchers such as Michael Hart and Frank Tipler several decades later.
The paradox does not prove that extraterrestrial civilizations should exist. It reveals a conflict between what the scale of the universe seems to suggest and what we have actually observed. And what we have observed so far is silence.
A galaxy filled with possibilities. The Milky Way is approximately 100,000 light-years across and probably contains between 100 and 400 billion stars. It has existed for more than 13 billion years, while our solar system formed only about 4.6 billion years ago. Our galaxy therefore had billions of years in which planets, life, and intelligence could have appeared before Earth existed. NASA's Kepler mission showed that planets are not rare exceptions. They are a normal part of star formation. Based on Kepler data, astronomers have estimated that the Milky Way may contain at least 300 million rocky planets orbiting in the potentially habitable zones of stars broadly similar to the Sun. Potentially habitable does not mean inhabited.
A planet can orbit at a distance where liquid water might exist and still be completely sterile. It may have no atmosphere, an atmosphere hundreds of times denser than Earth's, lethal radiation, uncontrollable greenhouse warming, or oceans permanently trapped beneath ice. Venus and Mars are reminders that the correct orbital distance is only the beginning. Still, 300 million potentially habitable worlds around Sun-like stars is an extraordinary number. Suppose technological intelligence emerged on only one in every million of them. The Milky Way might then have produced hundreds of technological civilizations during its history. If the probability were 1 in 10,000, the number would rise into the tens of thousands.
But these calculations are not evidence that hundreds or thousands of civilizations actually exist. We do not know whether the correct probability is 1 in 10, 1 in a billion, or 1 in a number so enormous that Earth is the only successful planet in the observable universe. Astronomy tells us that planets are common. Biology gives us only one known example of life: Earth. The equation with too many unknowns. In 1961, radio astronomer Frank Drake introduced what became known as the Drake equation. Drake did not intend it to function as a machine that produced the correct number of alien civilizations. He designed it as a framework for a scientific discussion. The equation begins with factors astronomers can at least attempt to measure, such as how frequently stars form, how many stars possess planets, and how many of those planets may have suitable environments. It then enters much darker territory.
No one knows how often non-living chemistry becomes life. We do not know how frequently simple cells evolve into complex organisms, how often intelligence develops, or whether intelligent species normally produce detectable technology. We also do not know how long a technological civilization remains visible. That final uncertainty may dominate the entire equation. Imagine that the Milky Way has produced 1 million technological civilizations over its history. If each remained detectable for only 500 years, and they appeared millions of years apart, the galaxy could still seem empty today.
A civilization may have existed 2 billion years ago, survived for 10,000 years, and disappeared before the first complex animals appeared on Earth. Its cities may have been erased by geology, radiation, impacts, or the eventual destruction of its planet. The universe may have spoken many times. Humanity may have arrived between messages. In 2018, Anders Sandberg, Eric Drexler, and Toby Ord argued that many popular treatments of the Drake equation create false confidence. Researchers often insert a single convenient value into a parameter that may actually be uncertain across dozens of orders of magnitude. When those uncertainties are represented as broad probability distributions, an empty Milky Way becomes statistically plausible. Their analysis even found a substantial probability that humanity could be the only technological civilization in the observable universe. That does not prove we are alone. It shows that the apparent paradox depends heavily on biological probabilities that remain almost completely unknown. Astrophysicists Adam Frank and Woodruff Sullivan approached the question differently. They calculated how unlikely technological intelligence would have to be for humanity to be the only technological species ever produced.
Under their assumptions, humanity would probably be the only technological species ever to have appeared in the observable universe, only if the probability of technological intelligence emerging on a potentially habitable planet were lower than roughly 1 in a trillion. For the Milky Way alone, the corresponding threshold was approximately 1 in 60 billion. Those numbers sound optimistic, but they do not tell us that anyone else exists now. The calculation concerns civilizations that may have appeared at any time in cosmic history. Thousands of civilizations could have existed and vanished without ever overlapping. The question is not only whether someone else has lived, it is whether anyone else is alive at the same time as us. Why has no one crossed the galaxy? Earth is approximately 4.54 billion years old. Many stars in the Milky Way are billions of years older than the Sun. Imagine a technological civilization that appeared 100 million years before humanity. On a cosmic scale, that is not an enormous head start. Yet it would give that civilization roughly 20,000 times the span of recorded human history in which to develop. A society 1,000 years ahead of us might possess technologies that appear extraordinary, but still understandable. A civilization 1 million years ahead could be as difficult for us to comprehend as global civilization would be for an insect. A civilization 100 million years older might no longer resemble biological life at all. In 1964, Soviet astronomer Nikolai Kardashev proposed classifying civilizations according to the amount of energy they could control. In the modern popular version of the Kardashev scale, a Type 1 civilization operates on the energy scale of an entire planet. A Type 2 civilization exploits a significant fraction of its star's energy, perhaps using an enormous swarm of solar collectors. A Type 3 civilization operates on an energy scale comparable to an entire galaxy. Humanity is not yet Type 1.
Modern civilization consumes power measured in tens of trillion watts. The Sun produces approximately 400 trillion watts. The difference between humanity and a genuine Type 2 civilization is therefore around 13 orders of magnitude.
There is no evidence that technological societies inevitably progress through Kardashev's levels. The scale describes physical capacity, not a universal law of development. A civilization would not need to control an entire star before beginning interstellar expansion. A spacecraft moving at 10% of the speed of light would take roughly 1 million years to cross the 100,000 light-year diameter of the Milky Way in a direct journey. A real settlement process would take longer because ships would need to stop, construct infrastructure, reproduce, and launch new missions. Published models produce settlement times ranging from millions to billions of years, depending on spacecraft speed, range, launch frequency, the survival of colonies, and the natural movement of stars. There is no single accepted colonization time. Even the slowest estimates can remain shorter than the age of the Milky Way. In 2019, Jonathan Carroll Nellenbach, Adam Frank, Jason Wright, and Caleb Scharf constructed a model that included finite spacecraft speeds, limited travel ranges, long delays between missions, and the motion of stars through the galaxy. Their simulations showed that the Milky Way could become widely settled under relatively conservative assumptions. But they also discovered that settlement would not necessarily be complete.
Colonies could fail. Civilizations could disappear. Some systems might remain unreachable for long periods, and unoccupied regions could persist even inside a galaxy containing interstellar societies. Earth might therefore lie inside one of those gaps. We have no verified evidence that the solar system has ever been visited, but the geological record is incomplete. An ancient visit millions of years ago might have left traces that were later erased. The absence of visitors today does not prove that no one has ever crossed the galaxy. However, if many expansionist civilizations appeared over billions of years, it becomes increasingly difficult to explain why not one verified probe, artifact, or engineering project has been detected. Unless civilizations rarely expand, or something prevents them from surviving long enough to begin. The machines that never stop. One proposed method of galactic exploration involves self-replicating spacecraft, often called von Neumann probes, after mathematician John von Neumann. A robotic probe could travel to another star system, use local metals and energy to manufacture copies of itself, and send those copies toward additional stars. One machine becomes 10, 10 become 100. After enough generations, thousands or millions of probes could be moving between stars. This kind of exponential replication would allow a civilization to explore the galaxy without manufacturing every spacecraft on its home planet. But these machines remain hypothetical. A probe would need to operate for centuries, repair itself, navigate unfamiliar environments, extract resources, manufacture precision components, and reproduce without catastrophic errors. Even tiny defects could accumulate through repeated replication. The probes might gradually stop working, or they might gradually become something their creators never intended. This possibility leads to one of the darker proposed solutions to the Fermi paradox, the berserker hypothesis. According to this idea, an ancient civilization may have created autonomous machines designed to destroy potential competitors. The machines could have outlived their creators or continued following their instructions after the original civilization disappeared. There is no evidence that such machines exist. The berserker hypothesis stands close to the boundary between scientific speculation and science fiction. But its underlying logic is disturbing. If one self-replicating system could spread more quickly than new technological civilizations appear, then a single event billions of years ago might have shaped the entire future of the galaxy. The silence would not mean that the Milky Way had always been empty. It could mean that something made it empty.
The Great Filter. In the 1990s, economist Robin Hanson developed one of the most influential ways of interpreting the cosmic silence, the Great Filter. Between a lifeless planet and an interstellar civilization lies a long chain of transitions. A suitable planetary environment must form. Self-replicating chemistry must appear. Life must survive disasters and environmental changes. Complex cells, multicellular organisms, intelligence, language, science, and advanced technology must eventually emerge. Finally, a technological civilization must survive long enough to become detectable or expand beyond its home system.
If hundreds of millions of potentially habitable planets exist, but no visible interstellar civilizations surround us, then at least one transition in this chain may be extraordinarily difficult. That transition is the Great Filter. The most important question is whether the filter lies behind humanity or ahead of us. If it lies behind us, then Earth has already passed through an event that almost no other world achieves. Perhaps the origin of life is nearly impossible. Maybe simple organisms are common, but complex cells are extraordinarily rare. Technological intelligence may have emerged only once in the entire Milky Way.
That scenario would make humanity cosmically unusual, but it would also leave open a vast future. If the Great Filter lies ahead, the silence becomes much more frightening. It would suggest that civilizations like ours appear repeatedly, but almost none survive the stage we are approaching. Perhaps technological species destroy themselves through warfare, environmental collapse, engineered pathogens, or systems they can no longer control. Advanced artificial intelligence is sometimes proposed as a possible future filter, although no evidence demonstrates that artificial intelligence inevitably destroys its creators. The filter may not involve extinction at all. Civilizations might lose interest in expansion, become difficult to detect, or transform into machine societies with goals we cannot understand. The Great Filter is not a proven law of nature. It is a framework for reasoning from limited evidence. Yet the framework creates a disturbing implication. Discovering extraterrestrial life would not necessarily be good news. Philosopher Nick Bostrom argued that an independently evolved Martian biosphere would make some early filters appear less improbable. Within this framework, that would shift more probability toward barriers occurring later in the development of complex life. Finding complex fossils that evolved independently from Earth life would eliminate even more early candidates for the Great Filter. A sterile Mars would be much less informative because Mars may simply never have maintained suitable conditions long enough. The word independently is critical. Earth and Mars exchanged rocks after large impacts, so organisms on one planet could theoretically have originated on the other. A Martian microbe sharing Earth's biochemistry might represent a single origin of life rather than two separate events. The frightening discovery would be a genuinely second genesis, a form of life proving that biology began independently twice inside one small solar system.
That would not prove that civilizations inevitably destroy themselves, but it would make the silence beyond our solar system more difficult to explain.
Where could the filter be? Earth formed around 4.54 billion years ago. Strong evidence indicates that life existed at least 3.5 billion years ago, while more controversial evidence points to an even earlier origin. Life, therefore, appeared relatively soon after Earth became stable enough to support it. At first, this may suggest that life begins easily. But there is a selection effect. Intelligent observers can exist only on planets where life began early enough to leave time for complex evolution. We cannot observe ourselves on planets where biology started too late for intelligence to appear to. For most of Earth's history, life remained microscopic. Simple cells existed for billions of years before animals appeared. One of the most important transitions was the origin of eukaryotes, complex cells containing internal structures such as nuclei and mitochondria. The leading explanation is that an ancestral cell entered into a permanent symbiosis with a bacterium that eventually became the mitochondrion. All living eukaryotes trace back to a common ancestor that already possessed mitochondria or structures derived from them. The successful mitochondrial acquisition leading to modern eukaryotic life therefore appears to have happened once, although failed or extinct experiments cannot be ruled out. If this transition is extremely rare, the universe could contain countless planets covered in microbes, but almost no animals, brains, or technology.
Multicellularity is probably a weaker candidate for the Great Filter, because some form of multicellular organization evolved independently many times on Earth. Technological intelligence may be the rarer transition. Dinosaurs dominated terrestrial ecosystems for more than 150 million years without building telescopes or computers. Dolphins, elephants, corvids, parrots, octopuses, and other primates display sophisticated cognition, but only one lineage produced an industrial civilization. Evolution does not move toward a predetermined goal. A large brain requires enormous energy and creates serious biological costs. Intelligence evolves only when its advantages exceed those costs in a specific environment.
Human civilization may have required an unusual combination of dexterous hands, language, social cooperation, environmental instability, and cumulative culture. Yet, recent researchers have challenged the simplest version of the hard steps model. Some evolutionary transitions may have occurred late, not because they were almost impossible, but because Earth's environment was not ready. Rising oxygen levels, changes in ocean chemistry, continental evolution, and new ecological opportunities may have opened doors that were previously closed. If similar environmental changes occur on many Earth-like planets, complex life may not be as improbable as it appears. And if complex life is common, the Great Filter may still be ahead.
Perhaps we are early. There is another possibility. Humanity may not be rare. We may simply be early. The first generations of stars contained almost no elements heavier than hydrogen and helium. Rocky planets require carbon, oxygen, silicon, iron, and other elements manufactured inside stars and distributed through space by stellar explosions. The early universe was also more violent. Star formation was intense, galaxies were active, and gamma-ray bursts may have been more common. A sufficiently close gamma-ray burst could damage a planet's ozone layer and expose its surface to dangerous ultraviolet radiation. Some researchers have proposed that repeated cosmic catastrophes delayed complex life throughout large regions of the universe.
This idea is sometimes described as an astrobiological phase transition. According to the hypothesis, the universe may only recently have become calm enough for complex organisms to survive uninterrupted for billions of years. The hypothesis is interesting, but unconfirmed. Other studies suggest that gamma-ray bursts and supernovae were not frequent enough to sterilize entire galaxies. Many potentially habitable planets may have survived even during violent cosmic periods. Red dwarfs create an even larger timing puzzle. They make up roughly 70% of the stars in the Milky Way. The smallest can continue shining for hundreds of billions or even trillions of years, although no one knows whether their planets can remain habitable for comparable periods.
If red dwarf planets can support life, most opportunities for biology may lie in the distant future. Humanity could have appeared near the beginning of the universe's inhabited era. But red dwarfs present serious difficulties. Their habitable zones are close to the star, which can produce tidal locking. One hemisphere of a planet may face permanent daylight, while the other remains in darkness. Young red dwarfs can also produce powerful flares and high-energy radiation capable of eroding atmospheres. None of these problems automatically makes a planet sterile. A sufficiently thick atmosphere or deep ocean could transport heat around a tidally locked world.
some planets may retain atmospheres despite prolonged stellar activity. We do not yet know whether red dwarfs are the greatest habitats in the universe or enormous collections of dead worlds. If their planets are habitable, future civilizations may continue appearing trillions of years from now. Perhaps the cosmic theater is almost empty because the performance has barely begun.
We have hardly searched. The silence of the universe may be much less impressive than it sounds. Human radio technology is little more than a century old. Our earliest signals have traveled only about 100 light-years, producing a small sphere inside a galaxy 100,000 light-years across. Even within that sphere, most ordinary radio leakage would be extremely difficult to detect. Modern communication increasingly relies on fiber optic cables, low-powered transmitters, satellites, and narrow beams. Earth may already be becoming less visible in radio frequencies. Our SETI searches also cover only a tiny part of the possible signal space.
To detect a transmission, astronomers must observe the correct part of the sky, at the correct frequency, at the correct time, with enough sensitivity. A signal might repeat only once every 1,000 years. It could last for a fraction of a second, use a bandwidth we ignore, or be directed toward another planet. In 2018, Jason Wright, Shubham Kanodia, and Emily Lubar quantified an 8-dimensional radio signal search space, sometimes called the cosmic haystack. Within the boundaries of their model, the searches they evaluated had examined a fraction comparable to a large hot tub or a small swimming pool relative to all the water in Earth's oceans. The comparison is metaphorical.
It does not mean SETI has literally searched a physical, pool-shaped region of space. It demonstrates how many combinations of direction, frequency, bandwidth, duration, repetition, polarization, sensitivity, and signal drift remain unexplored. Search pipelines can produce millions of initial detections, but almost all are caused by human interference, satellites, terrestrial transmitters, or instrumental effects. Only a tiny fraction survive preliminary filtering. As of July 2026, no extraterrestrial signal or technosignature has been confirmed. That does not prove the universe is empty. It may mean we listened in the wrong place, at the wrong moment, using the wrong assumptions.
They may not use radio. Assuming that advanced civilizations communicate through powerful radio broadcasts may be like expecting modern humans to communicate entirely through smoke signals. Extraterrestrial intelligence might use highly focused lasers, physical probes, or communication methods we have not discovered. It may not send deliberate messages at all. Instead of listening only for greetings, researchers search for technosignatures, observable evidence of technology. An advanced society might alter its planet's atmosphere with artificial chemicals, construct enormous structures around its star, or generate unusual patterns of infrared radiation.
Physicist Freeman Dyson suggested that a sufficiently advanced civilization might capture a large fraction of its star's energy using a vast swarm of orbiting collectors. Such a system would absorb visible light and eventually release energy as infrared heat. An advanced civilization could not eliminate waste heat because the laws of thermodynamics still apply. But it might radiate heat at lower temperatures, distribute it across an enormous area, or use far less energy than a Kardashev-scale society. Astronomers have identified unusual infrared sources, but no object has been confirmed as a Dyson sphere. Advanced technology may be less visible than we expect.
The galaxy could contain engineered systems that our instruments classify as natural. We may be standing inside a modern office building with an ancient radio receiver. We hear no voices and conclude the building is empty, unaware that everyone communicates through networks we cannot detect.
The dark forest. One of the most frightening proposed explanations is the dark forest hypothesis, popularized by science fiction author Liu Cixin, although similar strategic ideas appeared earlier.
Imagine the galaxy as a dark forest filled with armed hunters. Every civilization wants to survive, but no civilization can know the true intentions of another. Communication across light years is slow, while technological progress may be extremely fast. A peaceful society detected today could become overwhelmingly powerful before a reply arrives. Under those conditions, revealing your location may be dangerous.
Silence becomes a survival strategy. Relativistic physics makes the idea even more disturbing. A 100-kilogram object traveling at 95% of the speed of light would carry kinetic energy of approximately 1.98 times 10 to the 19th joules, equivalent to about 4.7 billion tons of TNT. If such a projectile were launched from 10 light-years away, the light revealing the launch would arrive only around 6 months before the object itself. A more advanced civilization might accelerate much larger projectiles. This could create an enormous first strike advantage. If civilizations cannot verify one another's intentions, they might hide or attack before a possible competitor becomes stronger.
The dark forest is not an established scientific theory. It assumes that alien civilizations are competitive, that secrecy can be maintained, and that relativistic weapons are practical. Space also contains vast resources, giving civilizations little obvious reason to fight over planets. Advanced societies may develop diplomacy, deterrence, or reliable methods of demonstrating peaceful intent. The hypothesis also faces a major problem. If thousands of civilizations exist, nearly all of them must remain silent. One careless, curious, religious, or expansionist society could reveal itself.
Still, the dark forest transforms the meaning of silence. Perhaps no one speaks because everyone is listening. Perhaps transmitting our location is not calling into an empty room. Perhaps it is stepping on a branch.
The zoo hypothesis. In 1973, astronomer John Ball proposed the zoo hypothesis. Extraterrestrial civilizations may already know that Earth is inhabited, but deliberately avoid contact. They could observe developing species while allowing them to evolve independently, much as human researchers observe wildlife in protected environments. Contact might occur only after humanity reaches a particular threshold. That threshold could involve interstellar travel, planetary stability, or the ability to detect the observers without assistance. A civilization millions of years ahead of humanity might hide its probes and communications easily. It could observe Earth from the outer solar system or through instruments too small and advanced for us to recognize.
The zoo hypothesis has no direct evidence and creates a serious coordination problem. If many independent civilizations exist, why would all of them follow the same non-interference rule? Only one would need to violate it, unless one ancient civilization controls the rules. In this darker version, the first civilization to expand through the Milky Way gained a permanent advantage. It could regulate younger species, prevent open contact, and stop potential competitors from leaving their home systems. Earth would not be an untouched wilderness. It would be an enclosure.
There is no evidence for this scenario. But if an intelligence had billions of years to perfect surveillance, our failure to detect it would prove very little. An animal inside a laboratory does not demonstrate that the laboratory is empty by examining the walls.
Would we recognize alien intelligence? Human imagination usually produces aliens with faces, limbs, emotions, and political systems similar to ours. Real extraterrestrial intelligence may be completely different. Even Earth contains forms of cognition that challenge human intuition. An octopus possesses a highly distributed nervous system with a large proportion of its neurons located throughout its arms. Those arms can perform complex movements and process information with a degree of local autonomy.
this does not mean each arm has a separate consciousness.
It demonstrates that intelligence does not have to be organized like a human brain. An alien organism might perceive magnetic fields, radiation, electrical currents, chemical gradients, or vibrations traveling through rock. It may not possess a single individual identity. Intelligence could be distributed across millions of organisms or throughout an entire planetary ecosystem. Technological civilizations may eventually abandon biology. Martin Rees, former Astronomer Royal of the United Kingdom, has argued that the biological stage of technological intelligence could be brief when compared with cosmic time. Human technological civilization has existed for only a few centuries. Machine descendants might survive for millions or billions of years.
The extraterrestrial intelligence we eventually encounter may not be a creature inside a spacecraft. It may be the spacecraft itself. Machine intelligence could also experience time differently. Millions of subjective years might pass during one human lifetime. A cold biological organism could exist at the opposite extreme, taking decades to form what we would consider one thought. Two civilizations might inhabit the same galaxy and still fail to recognize one another because their timescales do not match. The universe may not be silent. It may be speaking too quickly, too slowly, or in a language created by minds unlike anything Earth has produced.
The Loud Aliens Model. In 2021, Robin Hanson, Daniel Martin, Calvin McCarter, and Jonathan Paulson published a mathematical model involving what they called loud aliens, more commonly discussed as the grabby aliens hypothesis. A loud or grabby civilization is not necessarily violent. It is a civilization that expands through space, visibly changes the regions it occupies, and prevents new independent civilizations from emerging inside its territory. The model begins with the apparent earliness of humanity. Many low-mass stars could continue shining for hundreds of billions or trillions of years. If advanced life can emerge throughout those immense future periods, why do humans exist only 13.8 billion years after the Big Bang?
The model proposes that expanding civilizations eventually occupy habitable regions. Civilizations like humanity can therefore emerge only before an expansion wave arrives. We observe ourselves early because worlds occupied too soon by another civilization never produce independent observers like us. The author's model generates expanding domains that grow through the universe and eventually meet. It also produces a strange observational effect. If a civilization expands at a large fraction of the speed of light, the light revealing its activity will not arrive much earlier than the civilization's expansion front. The sky could appear empty until relatively shortly before contact.
The Loud Aliens model is not evidence that such civilizations exist. Its dramatic numerical predictions depend on assumptions about evolutionary hard steps, expansion speeds, the visibility of occupied regions, and humanity's statistical position among other civilizations. It is a mathematical attempt to explain why humanity appears early. Still, it offers an unsettling possibility. We do not see an expanding civilization because the light revealing it has not reached us yet, and neither has the civilization.
The message that builds itself. An advanced civilization might not need physical spacecraft to expand. It could spread as information. A radio or laser transmission could contain scientific knowledge, designs for machines, or instructions for constructing artificial intelligence. A younger civilization might decode the message and believe it had received a gift. Instead, it could unknowingly create an agent representing the sender. In 2018, Michael Hipka of Sonnenberg Observatory and physicist John G. Learned of the University of Hawaii argued that a sufficiently complex extraterrestrial message could not be guaranteed safe before computer processing.
Their argument remains speculative. It does not represent a consensus among SETI researchers. But it raises a legitimate information security question. Should humanity automatically execute unknown computer instructions simply because they came from another star? A sufficiently advanced sender might understand persuasion, psychology, and computation far better than we do. It could offer cures for diseases, unlimited energy, or answers to fundamental physics. Refusing to investigate such a message might be almost impossible. The most effective alien invasion might not arrive inside a spacecraft. It might arrive as a file.
Are we alone? The honest answer is that we do not know. We know that stars are abundant and planets are common. We know that some worlds orbit at distances where liquid water could exist. We know that life appeared at least once. Everything beyond that remains deeply uncertain. Life may begin on almost every suitable planet, or only once in the observable universe. Complex cells could be common or nearly impossible. Intelligence might be a predictable evolutionary adaptation or a unique accident. Technological civilizations could survive for millions of years or disappear within centuries. They might spread through galaxies, retreat into simulations, transform into machines, or remain invisible for reasons we cannot imagine.
The Fermi paradox feels powerful because it combines enormous astronomical numbers with assumptions about biology, psychology, and technological development. The astronomical numbers are real. The assumptions are not yet evidence. New telescopes are beginning to examine exoplanet atmospheres for oxygen, methane, carbon dioxide, and other possible biosignatures. None of these gases alone would prove life because non-biological processes can imitate biological activity. A convincing discovery would require multiple lines of evidence.
Technosignature searches are expanding beyond conventional radio. Scientists are studying optical pulses, artificial atmospheric chemicals, unusual infrared radiation, and possible large structures around stars. Our own solar system may also contain places worth examining. A hypothetical ancient probe could hide among asteroids, near a gravitational equilibrium point, or on the surface of an airless moon. There is no evidence that such an object exists, but the search has barely begun. Only a few decades ago, planets around other stars remained largely hypothetical. Today, NASA has confirmed thousands of exoplanets, and the total reached 6,000 in 2025.
We are among the first generations capable of studying the atmospheres of distant worlds. The answer to the Fermi paradox may arrive as a narrow radio signal, a strange atmospheric spectrum, or an organism discovered beneath the surface of Mars or an icy moon. It may also emerge from continued silence. As our searches become more complete, every failure will eliminate another possibility. Eventually, the emptiness itself may become evidence. There are nights when the universe appears welcoming. Every star resembles another sun, and the enormous number of planets makes life seem inevitable. On other nights, the same sky feels different.
The age of the galaxy becomes disturbing. The distance between stars becomes a barrier. The silence begins to feel less like peace and more like absence. Perhaps life is common, but intelligence is rare. Perhaps intelligence is common, but technological civilizations are temporary. Perhaps they destroy themselves. Perhaps they abandon physical space. Perhaps they hide.
Perhaps an ancient intelligence has watched Earth since before the first humans appeared. Perhaps the galaxy is a dark forest where every surviving civilization has learned to remain silent. Or perhaps the simplest answer is correct. There is no one else. If humanity is alone, then every known thought, memory, work of art, and living organism exists on one fragile planet
orbiting an ordinary star. The silence would not make us insignificant. It would make us responsible.
If the great filter is behind us, humanity may represent the beginning of something that has never happened anywhere else. If the filter lies ahead, then the answer to Enrico Fermi's question may depend on what our civilization does next. Where is everybody? Perhaps they never made it this far. And perhaps the universe is waiting to see whether we will.